Okay, I see the live recording button.
Good morning, folks. Welcome to our next episode of the Viterbi webinar on digital technologies for COVID-19. Today, we have a very exciting panel of faculty from Viterbi that have been exploring droplet and airborne transmission. So I'm going to hand over to Professor Mitul Luhar from Aerospace and Mechanical Engineering and have him tell us about today's program.
Very good. Thank you, Bhaskar, for the invitation to present. We're excited to present some preliminary work on droplet and airborne transmission. Essentially, what we're trying to do is assess the 6-foot rule and perhaps even more so the occupation of enclosed spaces as we move towards restart. As Professor Krishnamachari said, there is a group of us involved. So there's Professor Bermejo Moreno, Agolfopoulos, myself, and Professor Ronnie from Aerospace and Mechanical Engineering, Professors De Barros and Van Weiss from Civil and Environmental, and Professor Neil Siegel from Industrial and Systems Engineering. And we've also had lots of fruitful discussions and input on the medical side of things from collaborators over at the Keck School of Medicine. Right, so you'll hear from all of us in turn. I'm just going to pass on to Professor Siegel now, Neil Siegel now, to set the stage essentially. So Neil, I'm going to advance the slides on your command. Right.
Well, thank you very much. And thank you everybody for listening. I'd like to start with a little disclaimer. This is very preliminary work. It's not been peer reviewed. Much of the data that's available about COVID-19, of course, is being shared before peer review and final publication so that people can try to extract some value from all of that data, and we're making this contribution in that same spirit. So let's go on to the next slide. So I'm just going to set the stage. Of course, COVID-19 exists. We have no certain approach to treatment, no vaccine yet. And it seems to us that one of the key social and economic issues facing the world is how to safely reoccupy the indoors, right? Indoors is where classrooms are. Indoors is where most of us work. Where we obtain professional services, where we see our doctor or our lawyer and all that kind of stuff. And we think that there's a lot of data that suggests that being indoors in the presence of COVID-19 is very different than being outdoors and warrants some special analysis, right? Basically, you have a closed environment, a module or whatever ventilation does. And so you have the possibility that even if you're apart from somebody, some distance, some canonical distance from other people in the room will over time fill up with droplets, and those droplets, if somebody is sick, can be bearing viruses. And that's very different than outdoors, where it's very clear that, you know, being outdoors and no walls and having the breeze and all that kind of dilutes things much faster than potentially indoors, right? And so outdoors, there's a lot of other people looking at the problem, and certainly it seems that some combination of physical distance and masks provide some reasonable level of protection, although exactly what mask and what distance warrants a lot of study. Tons of people are looking at different types of masks, although we have something new, I think, that we're bringing to the table that we'll talk about a little bit later about masks. And also the question of what distance. It turns out that the canonical 6-foot distance derives from a single study in 1934. Did you lose the presentation, or? Hang on, I have it over here.
It looks like we lost the presentation. It's no longer shared.
Yeah. So anyway, he'll bring that back up. Anyway, so in partnership with if you can go back a slide or two, there we go. So in partnership with the School of Medicine, our team is undertaking the study of the fluid dynamics of airborne droplets, right? There's a lot of data coming out now that says that airborne droplets that have virus in them is a very important mode of transmission. You all remember that very early on in January and February, we were all fixated on touching surfaces that an infected person had touched. But now it looks like this airborne mode is a very, very important mode mode. So we can use fluid dynamics to understand how these droplets move, how far they move, look at the events that cause these droplets, breathing and coughing and so on and so forth, and then use our models and our theory to look at how does that work in an enclosed room over a period of time. So if I could have the next slide, please. So we're going to look, as I said, at the social scenarios of closed rooms that are occupied by a group of people for socially meaningful periods of time. We're going to use a combination of theory and analytic models and experiments. We all know that theory and models without being based in experiments can give you misleading results because your models and your theory may not have accounted for everything, but it's equally true that experiments without theory and models can be completely wrong. History is full of that because you might end up measuring the wrong sort of thing. So we need this balance. So we have a mixture of theory experts and model experts and experimental experts on the engineering part of the team, all balanced by our partners from the Keck School of Medicine who are advising us on the medical thing. So what we're going to do is we're going to start with some near field measurements where we can very easily calibrate our models to the experiments. And then we're going to go to farther fields and look at the dynamics of filling the room over time and seeing what happens. Then we're going to assess various mitigations, physical distance, masks of various sorts, ventilation, internal barriers like plexiglass walls in the room, and continuous decontamination. And then we're going to pull that back with some help from the medical people to create estimates of social utility through validation or denial of various social hypotheses like the one you see in the fourth box there. And the idea is that we'll create things that people can use, hopefully for guidance. We hope to evaluate mitigations beyond masks and physical distance. We think that the rigorous application of fluid dynamics is very relevant. And we're already seeing some new things by bringing our fluid dynamics point of view to the problem. Every paper, for example, that we've reviewed about mask efficacy looks at how many particles are trapped going out or coming in. And obviously that's an important thing to measure, but we have seen nobody who's realized or measured the effect that for the outgoing droplets that do escape, the mask will likely slow them down. And as you can see in the little note there under the third box, our preliminary measurements say that actually the slowing down is of a very large magnitude and may turn out to be very significant to the health and social aspects of the problem. So with that, I'll turn it back to Mitu, who will introduce our next speaker.
Very good. Thanks, Ivan. Next slide. So actually, before we get going, I think Neil touched on this already, but the transmission of SARS-CoV-2 is usually delineated into two different mechanisms, droplet transmission. So this is via larger respiratory droplets that tend not to travel very far, but could get into people's eyes, or it could be something that's inhaled. Or these larger respiratory droplets can also contaminate surfaces. So there's transmission via direct contact. So this is droplet transmission is sort of short range and via larger droplets. This is an established mode of transmission for SARS-CoV-2, but increasingly there's evidence to suggest that airborne transmission, so this is now the presence of microbes within aerosols or droplet nuclei, so really smaller particles that can remain in the air for longer periods of time and just sort of hang out. So there's increasing evidence to suggest that airborne transmission may be important, particularly in closed rooms over a longer period of time. So what we're going to try and do is we're going to try and address both mechanisms in a way. And to do that, we're going to split our problem next. Could you please advance, Ivan? Into two different problems. So there's this near field problem, which might, sorry, Ivan, back a slide, please. So there's a near field problem and a room scale problem. So the near field problem is essentially to do with this sort of a droplet-based transmission or potentially airborne transmission, but in the near field. And then the room scale problem is primarily via the airborne route. So this is our current understanding. And so what we'll start with is just some very basic reduced complexity models. So next slide, please, Ivan. We'll start with some reduced complexity models that look at both the near field and the room scale, and I'll get into that in a moment. But we're also doing higher fidelity numerical simulations for both the near field and the room scale. So these are computational fluid dynamics simulations. And then in particular for the near field, our group is also doing some experiments, as Neil mentioned, to figure out the effect of masks. And the goal is to essentially assess the effectiveness of these combined intervention approaches, particularly over extended periods of time in indoor settings. And the types of interventions we're going to look at is spatial distancing, of course, the use of PPE, also look at HVAC systems in rooms, so ventilation, and physical barriers as well, eventually. Okay. All right, so with that, let's get started with the technical aspect. So with the reduced complexity modeling, Ivan, next slide, please. All right, so these are reduced complexity models that that I've been working on. And essentially the first model that I'll start with, these are pencil and paper models, essentially with, maybe right at the end, you throw it into a MATLAB script or Excel spreadsheet to generate calculations. But essentially the first model that I'll present is this well-mixed room model. And the need that this model addresses is essentially what are allowable contact durations, occupant densities, ventilation requirements, PPE, etc. And what this well-mixed room model does is it assumes that there's some occupant density per unit floor area, this N. There's some fraction of occupants that are infectious, P sub I. And there's some fraction of time that the infectious persons are active. So maybe talking, lecturing loudly, moving around, and things like that. And this distinction between active and inactive or passive is important because virus emissions are expected to increase dramatically in case of loud talking or lecturing. And then because there's so many possible configurations that might show up, people might be moving around and there might be infectious persons might be on the bottom left, on the top right, things like that. Rather than sort of accounting for all of these details to start, what we assume is perfect mixing. We basically say that there's some amount of viral load that's being released into the room, and that's essentially being perfectly mixed across the room because of the action of people moving around, because of the action of any ventilation, things like that. And then from this, what we can predict is an average airborne virus concentration. And from that average airborne virus concentration, assuming HVAC is bringing in fresh air and taking away contaminated air, assuming people are wearing masks with different filtration efficiencies for inhalation and exhalation, from these airborne concentrations, and assuming people are breathing in this airborne virus, we can compute an average exposure or viral dose D. So how much virus are you expected to breathe in over a period of time given these parameters? All right. So with this, our model predicts when we run through the analysis. Next slide, please, Ivan.
Can you see the next slide, too? I'm on the output.
Not yet. I still see the schematic slide.
Okay, I moved to the next one. Maybe I can try to stop sharing and share again. Just try it again. This is the one that you wanted, right?
At least for me, it's still pulling up.
Okay, let me just.
Yeah, on mine it shows just a blank screen.
So let's try again. Is it still blank for you, or do you see the well-mixed room model implications?
Yeah. Perhaps what I can do, Ivan, is I can pull up the screen. That's okay.
Sure.
Yeah. Okay, there we go. All right.
Yeah, that looks good.
Does everybody see? Okay, very good, excellent. So when you do the math for this, this is what the average exposure or viral dose predicted turns out to be. So the average dose essentially increases linearly with the density of people in the room, right? So essentially a higher density implies a higher number of potentially infectious people and a higher viral load in the room itself. Increased ventilation rates from the HVAC system lead to a reduction in steady state concentrations and dose. So more highly ventilated rooms lead to faster removal of aerosols that are potentially virus laden. And then virus intake increases linearly with the duration of exposure. So clearly a 1 hour lecture versus 8 hours in an office or a lab together, it will lead to different exposures. Now, the key thing is this, that the virus dose depends strongly on the filtration efficiency of the masks as well. So the effects of inward protection, this F hat, are compounded by the outward protection. So outward protection limits the amount of virus that's floating around, and inward protection further limits how much a person is likely to breathe in, right? So with this model, assuming, getting estimates for virus emissions for active and passive persons from previous literature, what we can do is we can generate predictions that look a little like this. So this particular set of results now assume 1 in 10 people in the room are infectious. In the different columns, you see different ventilation rates. So HVAC with 2 changes per hour is not very well ventilated. HVAC with 4 changes per hour is the ASHRAE requirement for a classroom, for example. And HVAC of 8 changes per hour is highly ventilated. There's 2 different rows for different infectious in different activity rates. So infectious persons are either active 10% of the time or 50% of the time. And then each individual plot shows an average spatial distance. So how far apart people are in this room. And on the vertical axis is a mask filtration efficiency. We assume that for inhalation and exhalation, this is about the same. And I show a few key, so I show a couple of different important features here. So the vertical dashed line shows the current 6-foot rule, and the horizontal lines show a 50% mask efficiency and a 95% mask efficiency. So 50% you may think of as sort of a cloth mask, and 95% is closer to what you might expect for an N95 respirator. And what these contours show is the average virus exposure in terms of RNA copies inspired over 1 hour. So of course, if it's a longer period of time, the numbers will increase linearly, right? And what I would interpret these results as is sort of a risk of transmission. Certainly where there are no contours, risk of transmission, airborne transmission is low. But by the time you're getting to an average exposure of 50 or 100 RNA copies, maybe there is non-significant transmission risk. And all of this is with the caveat that essentially viral load and respiratory emissions and minimum infectious dose remain uncertain by as much as factors of 10, right? So what I would interpret this as is essentially at least a relative measure of risk. So if we think that HVAC with 8 changes per hour, 50% mask efficiency and 6 feet spatial distancing is okay, then you can sort of read across to similar contour levels in the other charts to evaluate relative risk. Closer to home in terms of what we might expect at USC, you can also interpret this in the context of a classroom. Say, similar results, you can have a classroom with 10 people, 1 of which is infectious, so similar infection rate. And then we can evaluate the scenario where maybe we have an infectious student who's only going to be asking questions maybe 10% of the time, versus an infectious lecturer that's talking loudly 90% of the time and perhaps even walking around, right? And so in that case, you see that the infectious lecturer case leads to a substantial increase in risk. And again, you can figure out what your comfort level is, but certainly when you're getting to average virus exposures of several hundred based on this model, I would be concerned with something like this. Okay, so these are just sample results from this well-mixed room model. What I should say actually is that this is just indicative of how rapidly the COVID research community is moving. An update basically a couple of days ago, and there's an update this morning. A very similar model was just made publicly available by indoor air quality experts. And you can access this at this public spreadsheet here. And you can evaluate a few different scenarios online. So if you're interested, I highly recommend checking this out. And it goes over some of the subtleties of the model as well, which I won't be able to cover here. Okay, very good. Now, one of the things that's important is the near field. Remember, the well-mixed room model essentially assumes that all this virus is spread everywhere throughout the room. So clearly, if you're close to an infectious person, the risk increases. And so here, what we've also developed is a very simple near field model, which assumes a plume, a turbulent jet, essentially, of these virus emissions. And it assumes that maybe you're standing right in front of this plume, so you're in the direct line of attack for this plume. And again, using similar input. So here, it's how far away you are from the infectious person, the fraction of time the infectious person is active, and filtration efficiencies, duration of exposure. You can calculate this viral dose. And here, as you can expect, compared to the case of being in a room, if you're standing for 5 minutes in front of an active person that is infectious, your exposure levels are much higher. So if you're standing at 2 meters away and you're wearing a decent mask, you're both wearing a decent mask, maybe you might argue that you're okay. But really, it's the 95% masks that are safest. And if you go to 10 minutes in front of this active person, then risk increases again. But I want to emphasize here that these are simple models, and viral load and respiratory emissions and minimum infectious dose remain uncertain. Right? Okay, so with that, what I'm going to do is hand over to Paul Ronnie, who's going to talk about experiments, and in particular, what happens in this very near field. What happens immediately after the mask? Okay, so Paul, take it away, please. Paul? We're having a hard time hearing you. Perhaps while Paul gets set up, what I will say is I'll start introducing the problem, which is these are experiments done in Professor Egolfopoulos's combustion and fuels lab, and they involve a technique that's known as particle image velocimetry. Paul, let us know when you're back. We still don't hear you.
For what it's worth, Paul, sometimes there's a different mute button on a keyboard or something that's not the Zoom mute button. So you may have like another hardware mute.
Okay, so I was using my headset. Can you hear me now through this microphone?
Yes.
Oh, okay. For some reason, you're not hearing me through my headset microphone. Anyway, unlike my assistant Cavalier here, that you and I can become infected with coronavirus. And so this work is actually focusing on Egolfopoulos's. It's not mine at all, but he wasn't able to attend today, so I'm speaking on his behalf. I'll talk about our work a little bit later on. All right, go ahead to the next slide. All right, so the idea is that what we really don't have a good way of modeling the amount of droplets that would come out of a person. So we're just going to use some experimental data on that, starting with just first, not a person, of course, because then we have to go through all the procedures that you need to use for human subjects. But first, we just use kind of a simulated human, and we'll look at what happens in the near field, and particularly what happens when you put a mask in front of that person, and how that affects the flow of air as well as droplets around that person. And then that will be coupled to the far field, that is the room scale simulations that include all the transport and evaporation of droplets, something that'd be very difficult to do experimentally, but is more amenable to computational simulation. So first of all, the effect of masks or any cover on the spread of droplets has not really been studied systematically. There've been a sort of a lot of anecdotal or empirical, I wouldn't even say empirical, but somewhat heuristic data on this. But in any case, what we'd like to do now is that the most masks outside of the medical community are designed to protect the wearer. For example, if you're working on tile and you're producing a lot of dust, you want to protect the wearer against inhalation. But now this is completely different. We need to protect people against exhalation. If we have an infected individual, we want to make sure that that person does not infect those around him or her. All right. So, but there really isn't a lot of quantitative information on the spread of droplets with and without a mask from a potentially contaminated individual. So some typical values, that is, if you're breathing and talking continuously, velocities have been said to be from 0.5 meter to 5 meters per second. Coughing and sneezing, of course, are much more violent events generating much larger velocities. We know that of course, the droplet number density would increase with exhalation velocity. A very large range of droplet diameters have been reported, and we want to try to incorporate, as well as number densities of droplets. And so we want to incorporate, find out what we can about how masks affect that, and then put that into the model of what happens when you have a room scale event. Okay, so again, the purpose of this work, to reiterate, is to provide quantitative experimental data on the effectiveness of masks and how it affects the velocity of exhalation as well as the number density of exhalation. Okay, next slide, please. Okay, so these experiments were carried out in Professor Yafopoulos' laboratory. The idea was simply to have a 1 centimeter diameter tube simulating a mouth, and which with exhalation velocities, steady state, so not breathing in and out, but just steady velocities from 1 to 5 meters per second. The results that we'll show in a slide or two are just for the case of 3 meters per second. And then particles on the order of 1 micron in diameter were introduced into the flow as tracers to see, how many particles are generated and where they go. And this was done with and without masks, which are called covers in what follows here. And then a pulse laser. Basically, the way that you do these experiments is you create a sheet of, you use some optics to turn the laser beam into a sheet of laser light, and then you produce a pulse of this laser light, very short duration pulse, and then you look at the light that's scattered off of these particles, and by seeing how they move as a function of time, you can then determine the velocity at these various locations, as well as get some estimate of the number density of the particles. And under these conditions, it's always an issue is, do the particles actually track the air or not? Under the conditions we're using here, relatively low velocities, relatively low shear rates, it's a pretty good assumption to say that these particles are actually following the gas flow. And you'll see that these results are I think, quite interesting, have not really been reported in existing literature. Okay, next slide. Okay, so here you see the flow from left to right, and then the laser sheet is being, the laser's coming up from below here. And you can already see in this image, you can see that these vortices are being generated by the flow. And so this is the case without any mask. And you can see that there's a lot of particles here. The incoming airflow has been seeded with these particles. And again, you look at the light that's scattered off of it. You look at it now and you take a snapshot a little bit later, and then you can do some fancy statistics to identify which particles moved where and get some velocities. Just one example of this is shown. So here's the radial velocity or the radial profile of the axial velocity component. So this is the component of velocity flowing, moving from left to right, but this is a traverse in this lower figure of what's happening from, you can see that Cavalier is quite interested in this, that flowing from, you're seeing a radius of 0 means the center line of the jet, and you can see that the jet velocity is higher in the middle than it is on either side, which is of course quite normal. And the other thing to see is that there's a shot-to-shot difference. You do the experiment over and over again, but because the flow is turbulent, every time you do the experiment, you get a little bit different result, but then you can do a lot of averaging. And so what you can see is here is, as expected, the velocity is on average about 3 meters per second, because that was what the velocity was at the outlet. If you move farther and farther downstream, then of course that velocity will drop off and this jet will spread, so you'll see a wider but slower profile. Okay, I think that's it for this slide. Go ahead. Okay, so then Professor Gafopoulos and his team looked at 3 different types of masks. A dust mask, which of course is inherently made to protect the wearer against inhaled dust, a surgical mask, which is just the opposite, and then just a 3 layers of tissue. Okay, and although we don't have any quantitative data, you could see qualitatively that there was a very large difference, much less, many fewer particles with the mask than without the mask, as you would expect, although that hasn't been quantified yet, but just looking at the images, you can see that. So in order to do, because what they really wanted to do was see, well, what's the velocity field downstream of the mask and how does it compare with that upstream? And so in order to do that, they had to actually kind of put some sort of particles on the mask itself, so that when the air blew over it, those particles would then be shed off of the mask and you could follow those. And so what you found is based on the fact that there were so few droplets downstream of the mask, said that the escaping particles that get through the mask then do not scatter light effectively, or their number density is low, or they're smaller. All of those things would lead to a weaker signal. And again, maybe the number density is below the threshold of detectivity with the equipment that they had. Okay, so that's one lesson learned, is that as you would expect, the mask reduces the number of particles substantially, using the particles as sort of a surrogate for the actual droplets, respiratory droplets that would be exhaled. Okay, next, please. Okay, and so what you see here is that without a mask, that you have a velocity about 3 meters per second. And when you put that mask just a few millimeters downstream of the exit of the jet, that then looking at what's just downstream of the jet, you see the velocity is decreased by roughly an order of magnitude. The most for the dust mask and the least for the 3-layer tissue, but they're all very, very substantial decreases in velocity. Now keep in mind, what's being kept constant here is the mass flow. So you say, well, wait a minute, the velocity is lower, what happened? Of course, that means that a lot of the flow, instead of going through the mask, is just going around the mask. It's going up like this. Because obviously we need a certain mass flow because you need to breathe. You can't just make the mass flow 0 or we'll suffocate. So one thing that we'll have to do in the future is see, okay, what happens to the air that does go, that goes parallel to the mask instead of through the mask? But we can see that just downstream of the mask, there's a much lower velocity. And that, is a potentially big benefit, because even if you have the same mass flow, if you have less velocity, that means you have less total jet momentum. And of course, momentum determines how far that jet can spread. Okay, so let's see. Anything else I need to say about this? Okay, we mentioned all this. And then you expect that with the lower, this was for a relatively high velocity. We're not normally blowing at 3 meters per second when we're just engaging in normal speech. but we expect that for, let's say, if you're speaking quietly and using a microphone, we may find, for example, that using a microphone, so you don't have to be as much of an orator to a classroom. If you speak quietly into a microphone, as opposed to orating to an entire classroom, we may find that that also helps decrease this number of droplets and the spread of those droplets. And again, a cover we expect will be even more favorable. And so the ongoing work is to characterize different mask materials and shapes, determine again not just the velocities, but also the particle size and the distribution of droplet sizes within the exhaust. And then also, of course, eventually to see, well, how can we minimize leakage while still making the wearer comfortable so that he or she will continue to wear the mask. And I think, is that it? Okay, next slide, please. Okay, that's it. Thank you.
All right, so I'm going to continue with the beginning of the explanation for the numerical simulations. This effort is led within the group by Professor Ronnie, who just spoke to you about the experiments, also by Dr. Ashkan Davani and by myself. And Vitor, let's go to the next slide, please. So the overview of this effort is actually given in this slide. We are trying to use a multi-fidelity approach. Now, why multi-fidelity? Because the computational cost is actually influencing the modeling that we need to do for this type of simulations. Going back to the initial picture given by Professor Luhar, we are trying to do simulations of near field, short duration events on the left in this picture, but also of room scale, long exposure and multi-intervention dispersion. So these have different requirements in terms of the computational cost, and therefore we can afford different fidelity, physical fidelity for these simulations. The purpose here is to complement the experimental efforts by, for example, providing data in planes or 3D fields that may not be accessible fully by the experiments, and also to serve as a bridge to connect to the reduced complexity models that Professor Luhar mentioned before. At the moment, we are using a software that is commercially available, ANSYS Fluent, and it has capabilities for turbulence, heat transfer, and phase changes. It's licensed through Viterbi, both for teaching that we use extensively and also for research activities. And as I mentioned in the introduction, this is going to involve different people, including Dr. Ashkan Davani, a postdoctoral researcher in the Aerospace and Mechanical Engineering Department, and also some master students, Tianli Bai and Francis Del Campo Melchor, who are doing directed research in a summer program on COVID-19 related challenges. The facilities that we use for these efforts are the USC High Performance Computing Center and also the virtual desktop infrastructure provided by ITS Viterbi. So let's move on to the next slide, please. All right, so on the near field events, we are trying to follow a progression of simulation capabilities. And the main intention here is to be able to provide the basis for verification, validation, and certainly quantification that we'll touch upon a bit later. So what you see here is a sequence of simulation capabilities starting from low Reynolds number, steady 2D jets. And this is shown here on the right panel, comparison with experiments. These are representative of breathing or soft talking. And then on the bottom left, what you see is the next step, which is the turbulent axisymmetric jets. These are steady jets for now. And again, you see two panels on the bottom left. One of them corresponds to the horizontal velocity of the jet as a function of the radial distance away from the center line. And you see the comparison between the experimental data in blue and the solid line, and then the simulations using a particular turbulence model, K epsilon model. And then on the right, kind of the center, sorry, on the right to that panel, kind of the center of the figure, you see another quantity that is measured in the experiments and compared against the simulations. In this case, the case rate of the centerline velocity. So On top of that, we are planning to continue with this progression, including scalar transport, multi-phase jets, and then evaporation and the effect of masks and shields. Let's move on to the next one. I think Professor Ronnie is going to continue now with the explanation of additional simulations. So please, Paul, go ahead.
Okay, can you hear me?
Yes.
Okay. All right. Yeah, for some reason, the microphone in my headset isn't working today. It's always worked in the past. Anyway, so the idea here, as I mentioned before, is to go from the experiments in the near field, and I saw that there was a comment about the wind noise. I'm sorry, because I'm using now the computer microphone and not my headset. It doesn't have any wind canceling device, so you'll have to bear with the wind noise, which of course I can't hear when I'm speaking. In any case, that we wanted to compare just for this initial test, just to show our capabilities and what we're working on, is we're going to look at the dispersion of droplets in a simulated cough, again, modeled using ANSYS Fluent, and compare the results in an open space and an enclosed space. Basically the same volume, but with just with walls, with impermeable walls versus with no walls, so that droplets that reach the wall just simply escape. And something called the discrete phase model is used in the simulation. I don't think the details are important here, except to say that there's unsteady particle tracking and includes a lot of features in this model. For example, some statistics on the collision of droplets and their coalescence and breakup, and their interaction with turbulence. And we also include heat and mass transfer because we have a relatively warm exhaust from the person into a room temperature room. And so there'll be some heat transfer, and that will affect the rate of evaporation of the droplets. So again, these droplets they're moving, they're falling due to gravity, and they're evaporating. So all these things, and they're also colliding with each other and also breaking up. So all these things are included in the simulations. And the droplets themselves, for the time being, are just being modeled as pure water, not water vapor, of course. The droplets is water, and the surrounding is air with a relative humidity of 50%. But of course, these are parameters that will vary in future simulations. Okay, next slide, please. Next slide. Oh, thank you. Okay, so here is the simulation for open space. So what you're seeing here, the color coding is with respect to the size of the particles. And you'll see on the left there, the scale gives the particle size in units of meters, so that the smallest ones are in the order of a few microns. The largest ones are like 300 microns. And so you can see, of course, that the smaller droplets, the blue ones, will stay suspended for much longer than the larger droplets, the red ones. And so you can see in this, even in this open room, that the droplets do disperse. And this is actually, let's see, the total amount of ejected, it's not injected, but ejected mass is shown there. So 18 grams per second for a tenth of a second, which is again intended to simulate a simulated cough. The computational domain, you can get an idea just from the size of the simulated subject there, but the room is 4 by 3 by 3 meters. And again, it's this is actually from a 1 centimeter radius circle located above ground level. And the whole distribution, we're not just using one droplet size coming out of the simulated mountain. We're using a whole range of droplet sizes that follows a distribution that was suggested by some previous medical experiments that predate the whole COVID-19 affair. And what you saw there is just 2 seconds. This is what happens at the end of 2 seconds. I don't know if you can play the movie again one more time. Okay, yeah. So you can see this is a total of 2 seconds of real time. So the movie is like 23 seconds long, so it's slowed down by a factor of 13. But you can see just even, the immense spread over this short period of time. And droplets as large as 20 microns can spread most of the way across the domain after only 2 seconds. Oh, okay, next slide. Okay, and then this is an enclosed space. Since these were just initial calculations, they're quite computationally intensive. So this is only 2 seconds of physical time in the simulations. And over this period of time, there really isn't much difference between the enclosed room and the open room. But what we'll see is, as we run these simulations longer, if that is the case or not. So if you don't see much difference between this video and the previous one, again, that's just because it's a very short duration simulation, but we will continue these for a much longer period of time. And we actually have done some of that, but we didn't have a good one-to-one comparison between the two. So you do see, of course, over a longer period of time, the difference between an enclosure and no enclosure is quite substantial. But again, we didn't have a one-to-one comparison, so I didn't want to show those quite yet. Okay, next slide. Okay, and you can see that even over a 3-second period, the amount of the total mass of particles, which of course is somewhat related to the total number of virus particles contained within those droplets, decreases by quite a bit, by over 50% in just 3 seconds. So again, it shows that these smaller droplets that stay suspended much longer are probably going to be the most worrisome and hazardous means of spreading the coronavirus. And so one of the next things we'll try, after looking at these same simulations, but for an extended period of time, is to see what happens with a breathing cycle. Because a cough or a sneeze is a relatively singular event, doesn't happen that often. And when you do have one of those events, generally people will try to cover their mouths or look away or something like that, which may minimize its effect. But just the general breathing or talking, of course, that's continuous. And what we want to see is, and we suspect, we'll see if it's true or not, we think that will be actually a more hazardous condition. So one of the things we'll do is simulate a complete breathing cycle. And I think that's all I have for that. Thank you.
All right, so I'll mention a few words about the uncertainty quantification, and this effort is led by Professor Felipe de Barros and myself as well within the team. So Mitu, please, let's move on to the next slide. So one important consideration when doing any simulations, but in particular for this type of simulations that are going to target room scale events that we don't have experiments to contrast with. So one of the important components is how to assess confidence, evaluate the confidence in the numerical predictions. So for that, we need this component of verification and validation. And in particular, we have to account for a number of uncertainty sources. On this panel, you have 2 types, aleatory and epistemic. On the aleatory side, we have, for instance, the room layout that's going to change from different scenarios, the ambient conditions, the efficiency of the mask filtration, the settings of the ventilation system, air conditioning system, breathing rates, even the human behavior, for example, in a supermarket, in a classroom setting, auditorium, and so on. And then on the epistemic side, we have things that, in principle, we can reduce the uncertainty if we had, for instance, better fidelity, better models, but it is not always possible because, as I said before, on the numerical simulations, sometimes it's the feasibility and the cost associated with these simulations that dictates what physical fidelity you can afford. So in this category, we have things like the turbulence model or the multi-phase model. And epistemic uncertainty also affects experimental measurements. So we have these 2 main components. On the right panel, again, you have the turbulent asymmetric simulation. And here I'm just showing you the comparison between 2 different turbulence models and the reference data. So what you see is the original picture that I showed you before with the K-epsilon turbulence model, which agrees relatively well with the experimental data. But you can also see that if you use a different turbulence model, for example, here, the K omega model, with a particular set of settings, your prediction is not going to be as accurate as before. And if you are using K omega, for instance, later on in other room scale simulations with the same settings, you may incur this error that you need to account for. So this is just one example, but you can extrapolate to many other examples as well. So we have two use cases for uncertainty quantification. The first one is the propagation of uncertainty sources, aleatory and epistemic, to assess the margins of operability, the margins in the outputs, in particular in regards to the exposure that Professor Nitul Luhar was mentioning before in the models. So with this, we want to be able to answer questions. For example, what is the probability of exceeding a safe droplet or aerosol concentration? What is the likelihood of droplets going beyond the 2-meter safety guideline for physical distancing? Or overall, what is the risk of infection in a given setting, indoor setting? Then there is a second use case, which is called the inverse uncertainty quantification. And this is meant for calibration of model parameters using experimental data, or for correction of biases. You may have systematic biases that you need to address in your simulation or modeling efforts. And the method, again, it depends on the complexity and the cost that you can afford for your simulations. So Monte Carlo type UQ is quite common in the literature, perturbation theory, polynomial chaos, and so on. So we are considering a range of these methods for VV and UQ. So let's move on to the next slide. So with this, I guess we've come to the end of the presentation. This is just a summary and some comments of ongoing work. So we have these three components, as we have emphasized in this presentation: the reduced complexity models. These are simplified analytical models that have been developed so far. And the purpose is to estimate exposure in both near field, but also at room scale problems. Preliminary predictions, as shown by Professor Luhar, are re-emphasizing the importance of these spatial distancing guidelines and the use of masks, facial coverings. But they also provide this guidance for engineering control, for example, the ventilation, air conditioning systems. There is ongoing work now on the verification, validation, and uncertainty quantification in combination with simulations and experiments, and also trying to find ways to bridge the two models for the near field and the room scale settings. And potentially, the idea is also to account for human behavior. In terms of the experiments, as Professor Ronnie explained, there are preliminary measurements that are showing that the masks are efficiently reducing the number of density of escaping droplets, the number density of escaping droplets, but also importantly that they decrease the forward velocity of this flow and the droplets that escape from the masks. So these two effects are indicative that the masks are probably more effective than originally thought or presently believed. And again, there is ongoing efforts, so both on reliably measuring the droplet size, the distribution of escaping droplets for different types of masks, and then the characterization in detail of the near field flow and the dispersion of droplets, so that we can incorporate that as initial conditions and boundary conditions for numerical simulations. And finally, on the numerical simulations front, we are exploring both near field and room scale simulations of this droplet and aerosol dispersion. We have initiated that for violent events, and now we are progressing towards more sustained events in room scale settings. And again, we have verification, validation, and UQ going on, and then we are trying to bridge with the reviews or the models as well. So in the end, there is an effort that needs to take place to integrate all these different components to make the study comprehensive and to provide better recommendations and guidelines. So with that, maybe let's close it here and then open the door for questions and answers.
Great. So we have some questions posted in Q&A, and I would encourage our attendees to post any other questions they may have there. So the one question has to do with if any consideration is given to exhaled particle and or infectious particles free in ambient air for inhalation, adherence to mask materials, which should affect the dropout percentage exhaled versus escaping filtering. So I guess it has to do with sort of adherence of the particles to the mask materials.
Right. So I think, let me take an initial pass on this. I think the efficacy of masks in general is dictated by multiple different mechanisms that are quite complicated. So in some sense, the masks can just serve as sort of physical barriers, but then electrostatic forces and things like that also become important, especially as you get to smaller and smaller droplet sizes. So perhaps this doesn't exactly answer the question that was posted, but I think sort of a detailed modeling of adherence and electrostatic forces and things like that is going to be very challenging. I can point people, if they're interested, to some recent papers on mask filtration efficiencies for different droplet sizes and things like that for a variety of different mask materials, including cotton, silk, everyday masks, if that would be helpful. But I think at least for now, we're not planning to do any detailed modeling of what happens at the mask. And we're really just going to use the experiments to serve as sort of the boundary conditions for our numerical simulations. This is a simplification, but in some sense it's necessary since we want to look at what happens over much larger scales and much larger periods of time.
We have a question from someone who's discussing a skin therapy business and asks if they should cancel the warm steam for opening pores because it might be acting as a propellant. I'm not sure if you may have any thoughts on that.
Perhaps if there's more on, I'm unfamiliar with the skin treatment. I suppose the concern is that the skin treatment might serve to spread airborne emissions a little bit more. I would hesitate to answer since I'm not 100% sure how powerful this steam treatment is, how much dispersion it is likely to cause, and things like that. In general, I would say if there is an infectious patient and there's respiratory emissions, viruses, in some sense, mixing it all over the room is better than sort of confining it to the near field. But that's a very, very qualitative recommendation.
Are there any modeling studies for medical procedure rooms, such as surgery, endoscopy, bronchoscopy, et cetera? So it's sort of more geared towards the medical domain?
Yeah, that's a good question, and certainly I haven't seen any so far. But as we all know, this field is moving very quickly. So I know we have a couple of medical experts on the line, or folks from Keck if they want to jump in. I don't know if there's much done on how much virus emission can be expected from some of these procedures and what the resulting risk is.
Just one brief comment. I'm not a medical expert. I'm just going to post a couple of links from prior studies, not specifically related to COVID-19, but they can still be related to different types of coronavirus. So again, the simulation that you saw, for example, from SimScale on one of the slides, it was not our simulation, but it's meant to simulate the flow in a hospital room with a patient that is infected and a medical doctor. So there is indeed ongoing efforts, maybe not only from SARS-CoV-2, but prior infectious diseases. So I'm going to try to post some links here on the chat in case they are helpful.
Great. If you folks are okay, let's take maybe a couple of questions since we have them here.
Yeah, if I could add just one thing about that actually Ashcan, kind of separate from this work, is also doing some work on the effect of, on looking at different sort of ICU configurations and different ventilation configurations. And as you might expect, that you get a better flow in terms of minimizing cross-contamination when there's like an exhaust duct near each patient. not surprising, but the simulation show it very graphically, in fact.
Sorry.
Sorry. So this is Daryl from I'm from Keck. One of the things that that we have here at the hospital is they basically rate rooms on how many air exchanges occurs within a certain time frame, and so they have a if they bring in a COVID patient into a room such as a MRI scanner or CT scanner, there is a minimum time that is associated, and that's calculated with the air conditioning team to figure out how many air exchanges there are. There are guidelines for that kind of situation. In terms of inside the medical facility, if you're going to be treating a COVID positive patient and doing procedures, that's actually more a matter of donning the correct PPE. In general, if they're going to be doing an aerosolizing procedure, they'll be given PAPR units as opposed to the N95 masks. But anybody that's going to be working in one of the designated COVID wards, here it's floors 7 and 8, they have to wear PPE before they get onto the floor situation. But so there are some guidelines for that. I don't know if there's been extensive modeling in terms of quantitative modeling. I think it's more of a question of air exchange and cleansing procedures. Some rooms get UV sterilization. Some rooms are just completely wiped down after use. They call it a terminal clean. And a lot of work is delegated to our incredible EBS environmental systems teams that go around and make sure everything is sanitized.
We have a question about the steps between the work that's happening and policy recommendations, I presume, for kind of the university classroom type of setting. How far are we from there?
We're working with folks in facilities who are deciding, making decisions on occupant density and HVAC ventilation rates and things like that. And so certainly the reduced complexity models are being used to assist in terms of decision making. So far, from what I've seen, their FMS is on the right track in terms of increasing ventilation rates above the minimum standards, providing effective inline filtration, and increasing fresh air fractions. But yeah, that's ongoing. That interaction is ongoing.
We have a question that's also asking if there are thoughts or plans to study similar parameters for face shield alone efficacy. So not masks, but shields, I guess.
I can speak to this as anyone else in the team, but I believe that's the idea, to consider not only masks, but also different face coverings, including face shields. And that is probably, from the simulation standpoint, a bit easier to accomplish because it's not a porous material, so it's just a barrier that is going to deflect the flow in a different direction. So going back to Professor Lujar's point about using the experiments to provide boundary conditions for the simulations, this is probably one simulation that can be done completely from the mouth, expelling the droplets all the way into the mask, or sorry, the face shield, and then deflecting the flow around. So
I'll be happy to provide you the face shields that we use here at the hospital, the ones that we created for emergency PPE construction, if you need those for testing.
Great.
And then one last question, perhaps. This is, I assume, from a concerned parent. With schools opening in mid-August, would you send your child into a classroom if you had a high-risk family member at home?
I guess this is a very personal decision to make. I wouldn't provide any recommendation, at least based on the simulations. If I were a parent, I would be very careful. That's the only thing that I can say, especially considering that there is options to do remote learning that USC in particular is addressing. So I think my personal take is, if you need to go, you are an essential person, then you go. But if you have concerns about infecting family member, relative, or anybody else, I think It's again a personal call, but there are options to learn remotely. I can say that the university is taking all the steps to make this process as safe as possible, but it is ultimately the responsibility of all of us to decide what the best strategy is given the circumstances that we live in, our families and our nearby people. So
Great. Well, I'd like to thank all our panelists and faculty who presented and answered the questions today. Really appreciate your joining us, and thank you again. Bye.